Hey everyone, welcome to The Explainer. Today we're unpacking exactly how Docker fundamentally transforms the software development lifecycle. But look, we aren't just going to sit here and talk theory, we're going to give you the actual, battle-tested fixes to survive using it in production. Because let's be honest, if you've ever felt the absolute pain of deploying a complex application only to watch it instantly break in production, you are exactly in the right place.
Let's just start with the oldest, most universally frustrating excuse in software engineering history. But it worked on my machine. I mean, we've all said it to save our own skin, right? And we've definitely all groaned in absolute despair when a colleague casually dropped that line on us during a completely botched Friday afternoon deployment. It is literally the battle cry of broken software.
So, the big question, how do we actually kill this excuse? Well, to figure out how we banish that phrase from our daily stand-ups once and for all, we really have to look at the root cause of the trauma. For DevOps engineers and developers alike, we have to figure out why code behaves so wildly differently from one laptop to a production server.
And you know what? It all comes down to the inconsistent environment. We're talking about those tiny, annoying differences in local development setups, different OS versions, hidden dependencies, and quirky configuration settings. It's a mess. In fact, to put this into perspective, a recent IBM report found that inconsistent environments account for over 40% of bugs found in late-stage testing. 40%. That is a massive failure rate that effectively just grinds your entire software development lifecycle, your SDLC, to a complete halt.
Okay, so let's dive into Section 1, the Docker Revolution, standardizing the software supply chain. For years, the industry was desperately searching for a way to package code reliably. And now, we finally have a solution. To really understand its massive impact, just consider this number: 90%. Over 90% of containerized environments today are running Docker. It has absolutely become the undeniable industry standard for packaging an application and its dependencies into one portable, self-sufficient unit. And this matters tremendously, because it means whether you are testing on a cheap 5-year-old laptop or deploying to a massive enterprise cloud cluster, the environment running your code is absolutely 100% identical.
But you know, to truly grasp the magic of Docker, we need to compare it to the old guard. In Section 2, containers versus virtual machines, the heavyweight versus the lightweight. Let's see exactly why the older method was holding teams back for so long. So here's the crucial point. Virtual machines, or VMs, simulate entire machines, from the hardware up. That requires a bulky, full operating system for every single instance, which makes them incredibly heavy. Containers, on the other hand, just isolate the application processes and share the host OS kernel. So think of VMs as buying a completely separate, fully furnished house for every single appliance you own. Crazy, right? While containers, they just efficiently share the plumbing and electricity of the house you already have. And this breakdown brilliantly illustrates the sheer efficiency gap between the two approaches. Notice how containers boot in literal seconds with minimal overhead, while VMs can frustratingly take minutes just to boot up an entire OS. Containers demand a fraction of the resources, and because they're so highly portable, they let you pack far more applications onto a single server. You are getting a much higher application density and way lower costs on the exact same hardware. It's a total game changer.
Let's move right along to Section 3, supercharging the modern SDLC. We're going to see how this speed, consistency, and focus on microservices builds into an absolute superpower for your entire engineering team. Because when you stop fighting your infrastructure, the results are just explosive.
I mean, the speed advantage is almost unbelievable. According to the 2024 DORA report, which by the way is widely considered the gold standard for tracking DevOps productivity, high-performing teams leveraging containerization deploy a staggering 973 times more frequently than their lower-performing peers, almost 1,000 times faster. Just think about that massive competitive edge for your product's time to market.
If you look at the stark contrast in the data plotted out here, the Docker-enhanced pipeline drastically reduces the time spent on coding, testing, and deployment compared to traditional methods. By giving developers isolated, perfectly consistent environments, you're essentially eliminating the agonizing debugging delays caused by environment mismatches. Everything just flows so much faster when the foundation is completely standardized.
And the benefits compound massively when we start talking about microservices. You gain independent microservice scalability, zero downtime rollbacks through precise versioning, and absolute environment parity from dev all the way to production.
Plus, think about this. A crash in one container, say your payment gateway goes down, it won't take down your user login container. It provides immediate fault isolation, which makes these complex, massive systems remarkably resilient and intelligent, especially when you pair them with load balancing tools like Kubernetes.
All right, but let's pause the hype train for a quick second. Let's look at Section 4, Real-World Challenges and Fixes for a much-needed reality check. Any seasoned DevOps engineer will tell you Docker isn't totally flawless. It breaks, and when it misbehaves in a live production environment, it can be an absolute nightmare. So let's fix the most common issues.
Let's run through some rapid-fire troubleshooting, starting with the classic bloated container that drags down your CI/CD pipelines. Massive images waste bandwidth, and they slow down every single automated test you run. So, what do you actually do when your image size is simply way too large?
Well, first, stop using those heavy base operating systems. Swap to a minimalist distribution like an Alpine or Scratch base image to immediately cut down that overhead. Next, combine your multiple run statements to drastically reduce your image layers. And finally, utilize multi-stage builds. Actually doing this will immediately trim gigabytes, literally gigabytes of fat off your image sizes by only keeping the required compiled binaries in your final production output.
Next up, picture this. You deploy what you think is a flawless update, and suddenly your container gets trapped in an infuriating infinite restart loop. It crashes, it restarts, it crashes, and it restarts again, driving your server load absolutely through the roof and throwing a massive wrench into your uptime metrics.
The fix here? Stop guessing. Check your Docker logs immediately to spot the exact entry point crash that's causing the failure. Furthermore, always ensure your restart policies actually make sense for the production workload. Set policies like on failure or unless stopped. Doing this prevents a single buggy line of code from perpetually consuming all your system resources, and it gives you back control.
Okay, challenge number 3. It's 2 a.m., your pager goes off, and you get a critical alert. What do you do when your Docker instances have silently eaten up your entire server disk with old uncompressed logs and dangling images, throwing that dreaded no space left on device error?
You have to be aggressive and intentional with your cleanup. Run a system prune command with the all flag to wipe out unused networks and orphaned images. Run a volume prune to clear out dangling storage volumes. And, if necessary, just move Docker's data root to a larger partition entirely. Automating these cleanup tasks so you don't have to do them manually at 2 a.m., that is exactly what separates the good DevOps engineers from the truly great ones.
Moving on to a classic networking headache that can literally stop a deployment dead in its tracks. What happens when a container straight up refuses to start because it throws a super frustrating host port conflict? Finding and killing the rogue process holding your port hostage takes maybe 2 seconds using the lsof command to instantly list all your open processes. Or, if you prefer a non-destructive route, you can simply remap your exposed container port to a completely new host port entirely on the fly. It is a highly flexible networking model once you really understand it.
Finally, we have to talk about the single biggest security sin a developer can commit when building a container. It's the exact kind of careless mistake that ends up causing catastrophic, headline-making data breaches. Are your secrets exposed in your images?
Stop committing credentials directly into your files. Seriously, never use the copy command to pull a .env environment variables file into your image. Baking API keys or live database passwords directly into your Docker file creates massive security vulnerabilities that any standard image scanning tool will flag immediately. Always protect your infrastructure by using proper Docker secrets or a fully encrypted vault.
I want to leave you with this brilliantly pragmatic thought from the dev community. The more you break Docker in testing, the less it'll break you in production. Use Docker to really push the limits locally, purposely find those edge cases, and ensure your production environments become totally unshakable. The tools for absolute consistency are right in front of you. So are you going to keep making excuses about your local machine? Are you going to containerize the chaos? Thanks for learning with me today, and I'll catch you on the next explainer.